Hi everyone. So I'm very happy to introduce today Melvyn Sim as our speaker. So he's a professor at the Department of Analytics and Operation Research of NUS Business School. His research is mainly focused on decision making and optimization under uncertainty. So for the robust optimization community, he's well known, especially due to his paper, The Price of Robustness, together with Dimitris Betsimas. And he's editor in several journals, for example, Inform's OR Management Science and Journal on Optimization. And we are very happy to have him here today. And please, Melvyn.
Thank you very much for the kind introduction and also for organizing this webinar. It's really my pleasure to contribute here. This is the second time I'm contributing here, and I really enjoy this session. Right. So the title of this talk is Occam Razor of Robustness. It seems to be a strange title, right? But before I do so, let me just acknowledge the contribution of my co-authors. We have James Chen Zhi. He's now in assistant professor in CHK. Jerry is a first-year PhD student at the Institute of Operation Research at Analytics at NUS. My colleague Xiong Peng, right? Zhi and Xiong Peng, we have developed the software together, and part of the reason why we came out with this research we want to write, we are actually doing a monograph, a book on robust optimization, and we want to go back to the basic principle. And while we are doing this thing, right, we want a simple introductory to robust optimization that can be applied in a lot of settings, right? And we thought that, and we just touched upon, why don't we just come up with a simple idea, right, that will work. And it turns out that there's some interest that led to this project. So the phrase Occam Razor, I kind of believe that most of you, if you are not sure, might have Googled this thing. It's more a philosophical razor or a rule of thumb, right? So this cartoon, this cartoon, Pout Higher Deeper, I think some of you might have seen it before. The Occam Razor is, what's the Occam Razor? When faced with two possible explanations, the simpler of the two is the one that is most likely to be true. From the professor perspective, there's the other side, right? Occam professor. When faced with two possible ways of doing something, the more complicated one is the one that professor will most likely ask you to do. Right? I think that's the same for referee as well, right? Okay, now we are all in this line as researchers. We all face the issue of publication, and we always been asked to do the tougher one. But there's some truth in this Occam Razor. Sometimes the simpler method could be the best. It may not necessarily be the case, but a simplistic idea here that use the least assumption here sometimes might be the most possible approach, right? So in the context of, say, machine learning, right, I would say that what would be an Occam Razor in machine learning, possibly a simple regression, right, where we do not make a lot of assumptions, right, just a linear model, and that's something that's ubiquitous and it's been popularly used, right, and that's something that we are looking at, right. So what do we think of the Occam Razor in the area of robust optimization? So let's look at some of the possible considerations, right? We should operate with minimal assumptions regarding uncertainty, right? So you want it to be as minimal as possible, because that kind of reflective about robust optimization where we don't really know what the distribution and so forth, right? And the other one, for it to be useful, right, it should align with the most important format in our field in OR, which should be the linear optimization format, right? That's the most popular, most important format that is used in the industry, right? There is software available for large-scale optimization. So I think appealing to this format is important. It should be intuitive to specify, right, the robustness. When we talk about robust optimization, we are not just looking at the worst case, we are looking at a family of solutions. We are looking at articulating at the level of robustness that we want. We do not want it to be over robust, right, or too fragile. So we want a spectrum that we can adjust. So for us to be able to articulate this level of robustness, and the trade-off is something to be considered as well. And the implementation should be straightforward. One of the issues that we would like to do, we try to extend is whether we can extend it to multi-period decision making. Multi-period decision making has always been a very, very tough problem to address. Is there a way, a simple way, right, based on minimal assumption that we can actually address those tractability issues, right, for multi-period decision making, right? So let's start off with a deterministic optimization model, right? Since I'm focusing on LP, I technically will look at a simple linear optimization model, right? But instead of looking at it from a linear optimization format, I'm going to write it in the form of where I have attribute function. The objective here is linear, right? But I have m attribute function, and this function is going to be polyhedral function, which I'll explain later, right? More importantly here, I focus on X being the here and now decision. In other words, decisions that once you solve it is going to be implemented now, regardless of whether I see the true realization of the uncertainty, right? I'm going to use, so Fm will be the attribute function, there are m of them, right? Within this m function, this attribute function, there'll be an embedded optimization model, which I'll explain later, right? And tau m will be the constraint, the constraints that will like this attribute, right? The attribute could be cost, it could be penalty, and so forth. I want that to be within control of tau m, right? So the in linear optimization format, the simplest one would be to look at a fine uncertainty. That's where the price of robustness, right? Where we started on linear optimization, I'll focus on by a fine attribute function, right? But so this is something that we all know, right? And z hat now is going to be a predicted input vector, right? In the sense of robust optimization, I'm not looking at a stochastic version of this prediction of z hat. I'm not, because in the sense that I'm looking at problems where you're only solving it once, you're probably not going to repeat it many times, so you don't really need to do expectation, right? It could be like, for example, in project management I mentioned, which I'll talk about later, where you have this one chance to get your solution right. You can't really repeat it, right? So, and that seems to be the gist of robust optimization, rather compared to stochastic programming, where you can evaluate risk. But here in robust optimization, we'll just look at these one-time decisions that you are making right now, and whether you would and the impelled solution will be felt later, but you can't really repeat the process under the same identical scenario again. So that's what we are looking at. And one example, I just give you an example of this framework will be to, for example, look at the project crashing problem. So in the project crashing problem, it is part of project management where I want to minimize the cost, the allocation of resources, right, so that the project can be completed on time. So if you are familiar with the project network, where each of the arc represents a precedent constraint, like arc ij means activity j can start after the task I concludes, right? So you can set up this problem as a network problem, right? In the crashing problem here, right? In the crashing problem, I try to reduce the duration of task. So I denote di as a duration of task I, right? But I could have incur a resource of x, right? Additional resource to reduce the duration by zx. Gix, right? X is a value between 0 and b is smaller than 1, right? So if x is 0.5 means I can reduce the time by 50%, right? But that would, by doing so, I'm going to pay a price because I'm actually incurring more resources to reduce the task time for that particular task. So project crashing problem will be to minimize the crashing cost and ensure that the project will be complete on time. So I can write this as a deterministic problem, right, as follows, right, and minimize the cost subject to f. F is the attribute relating that helps me compute the project completion time. So it's the completion time attribute, which is another minimization problem, right? So this minimization problem will take into account of what is the actual outcome of z, right? So z means the task, the time it takes for the task to be completed, right? And minimizing it will give you the earliest completion time for the entire project. Okay, so I can write everything as a single optimization problem, but doing so, right, I'll mix the here and now decision and the wait and see variable. This is not what I want to do, because sometimes when I remember in the early, when doing my when I presented my ideas, a lot of some of common queries which I get: how would robust optimization deal with equality constraint and so forth, right? And a lot of times at that time, when we look at a linear optimization, we don't look at which are the recourse variable, which are the here and now variables and so forth. We just have the deterministic model. And that doesn't give you information on what actually happens in the decision-making process, right? And for that, when you look at robust optimization on a linear optimization, you may not really know how the uncertainty responds to the problem. Like in this case, z, if z is different, right, y will take a different value, right? So in this case, y is what we call the wait and see or the recourse variable. So for that purpose, I don't really want to put it in a standard linear optimization framework, right? But write it in the form of multi-attribute problem, right? So let's try to generalize this attribute function further, right? I like the linear optimization format, so that just focus on the quasi-literal attribute function that can be written in this form. So in this case, y will be the wait and see recourse variable. In other words, the decision that's made after I see z, right, the uncertain parameter. And I'm going to focus on this affine map, right? This is A and B are affine map of z. So these are the common assumptions that we made in robust optimization, right? And you look at this function, the attribute function will be a convex function of z, right? But there is an issue with this formulation, right? If you look at the linear optimization, if you look at this problem, right, the objective may not be finite. If the problem is infeasible, right, the objective will shoot up to infinity, right? If the problem is unbounded from below, you'll go down to negative infinity. That is from the mathematical optimization perspective. In real attributes, you'll never get infinity, right? The optimization just grew up. The reason why it gets to infinity is because the model doesn't take into account of what actually could happen, might have happened, right, when constraints get violated and so forth. Usually we ignore those costs. But I would say that if you want to model robust optimization, it is important to ensure that the function, when you violate constraint, you must take into a contingency what actually happens when constraints get violated. It cannot be an infinite cost. It should be some finite cost, right? So for that reason, we put in impose additional constraint on this problem, right? Which we call connective recourse. It's very similar to complete recourse, but it's a weaker form of complete recourse, right? So that connective recourse satisfies two things. The attribute function is actually finite when evaluated on the predicted value, and that as z sub p. So the other condition is this just relates that this for every feasible for every uncertain outcome that deviates from z hat, the predicted value, I can find a feasible direction p towards that. So that just means that it's a weaker, less stringent than complete recourse. And with this assumption, right, the attribute function will always give you a finite value for every x, and more important, for every z in Rl, right? So no matter what happens to uncertainty, you are guaranteed that you're going to find a feasible solution. Okay. So let's look at the most common method of robust optimization is what I would call it. In fact, I would call it a local robust optimization method. When we look at robust optimization, you have a support set. looks at that ensures that all the uncertainties will be there, right? We also look at uncertainty set, which is smaller than the support set, right? So I call that the localized. I'm not sure whether I'm the only one to call it, but I will term it as a localized, robust optimization approach, where this U is an uncertainty set that's controlled by this parameter gamma that controls the size of uncertainty set, right? Importantly, this set, right, usually is characterized. It's actually written that it's actually formulated. It's a subset of the support sets, right? And more importantly, there's this. I'll call it the prediction disparity matrix. It's just a distance, right? A distance that measures from Z to the predicted value. How far Z can deviate from the predicted value. In the localized approach, right, we only look at uncertainty that's not too far away from the predicted value, right, specified by gamma. Okay. And the most common uncertainty set, I would say, used in robust optimization is actually the budgeted uncertainty set, right, which we I think is about more than 20 years ago when this idea was conceived. And at that time, I was still a student doing my PhD. Just in the first year, I tried to read the papers on robust optimization by Bentel, Nemirovsky, Alkawi. I couldn't really understand because I don't have a grasp of coding optimization and so forth. But I tried to think of something simple that I understand in LP. And that's how I look at it. So I look at a model where I can dictate the number of uncertainty, the coordinated number, the uncertainty that might deviate from the nominal value. And that is what we call right now as the budgeted uncertainty set. In the budgeted uncertainty set, we have a box uncertainty set, right? And we also have one norm, right? Disparity matrix. The matrix is actually measured in one norm. The reason is that this will keep everything as a polyhedron, right? So we want to keep everything as LP, right? And this D is the normalization metric. I'll talk about how you can determine this D matrix later, right? So the nice thing about here, you can articulate robustness using terms that people will understand. Gamma, right? If you look at how many uncertain, it's just a count of how many uncertain parameters that might deviate from the norm. So this turns out to be very, very popular, right? You mentioned in the introduction, it did mention that this is, the price is actually one of the most successful robust optimization model, right? And we look at it, why is it successful? I think I've done a lot of work. It's sometimes it's very, this is my first paper, and I realized that it's difficult to improve over this in terms of its popularity. So, but let's try to look at it. Why is it why do you think it's successful, right? I don't think it's the most sophisticated. All right, it's never the most. It's actually one of the easiest model, right? It's not the first robust optimization model because this is built under the work of Nemirovsky, Bentel, Alkawi. They have developed a truly more sophisticated way of looking at robust optimization from the coding optimization perspective, right? You look at it, this is just a simple case with a very simple uncertainty set, right? But I would argue that it has the characteristic of an Occam razor, right? It appeals to the most robust optimization format. At that time, when we introduced the robust optimization, we were more looking at the semi-definite programs, quadratic and so forth. That's technically very sophisticated, right? But the theory is that, right? Yeah, the other thing is that we can actually articulate the robustness using a simple idea that we call, Dimitri actually termed this as the budget of uncertainty, right? It's simple to implement and people find effective, right? I think there are also talks that stand it to bi-level and quite a lot of follow-up in terms of very creative application using this simple approach. But there are less attractive issues. If you're in the business school, I don't think you can teach this to an MBA student yet, right? Okay, for a reason, it might introduce some non-intuitive dual variables in reformulation and so forth. Specifying gamma could be an issue. I'll show later the solution changed roughly with respect to this parameter gamma. Right, the support set might be difficult to estimate. Right, if you look at statistical perspective, how do you estimate the support set? This is the tough problem, right? You can estimate variance and so forth, right? But if you want to look at the support set, is a string tail, right? And usually you don't have enough time, right, to do so. And more importantly, right, adaptive problem is still intractable. Of course, there are decision rules and so forth. But the question is, do we really need? Are there other approach that can circumvent that can address this issue when in multi-period problems? And I did mention about this this is still a localized robust optimization. When I talk about localized, it doesn't take into account of what happened if the uncertainty is outside this uncertainty set, right? Now, there are works that extend it to globalize robust optimization, right? And in globalized robust optimization, right, you don't have a restricted uncertainty set, but you allow uncertainty to change to affect globally, right? But you actually control, right, the level of violation by distance. So now the disparity matrix, right, the friction disparity matrix is now moved into the constraint, right? And this lambda parameter is a parameter that is specified that you want to control how much the constraint will be violated relative to the level of a distance, right? The distance from which the uncertainty deviates from the predicted value, right? Presumably, if the value is far off from the predicted value, you will allow some level of violation, right? But you control the level of violation by lambda, right? That's the parameter that you would specify. You specify lambda equals 0. It ensures that this will be always satisfied, which means is you get the worst case value, right? It turns out that this approach has one advantage. It's actually, if you actually try out and change value of lambda, you find that solution doesn't change too abruptly compared to the localized approach when you change the implied uncertainty set. But there's still issue in terms of how do you specify this protection parameter, right? Now, there's a variation of globalized approach, right? The GRC sum approach, or what I'll call the robust satisfying approach, right? And in this case, right, I add a term kappa over here that multiplies with this term over there, right? My goal is to minimize the contribution of the deviation, right, by minimizing kappa, right, as much as possible, right? So if there is ability to tighten, right, the robustness by minimizing kappa, I will do so, right? It turns out that here, in this robust satisfying model, right, the first thing you need to do is to specify V. So V is actually the solution to the deterministic optimization model, right? Then you specify gamma. In this case, gamma is the additional cost you would incur, right? You will be willing to incur to improve the robustness, right? So you can call this gamma really the price of robustness. How much robustness you want to add to the problem by articulating the price that we need to pay, right? When you set the price to gamma greater than 0, this will have more leeway, right, to minimize kappa, to make this as robust as possible, right? So this is what I call the robust satisfying approach. And from this, you can actually distill what is a decision criteria, what this thing tries to do, right? And you can distill the criteria which we call the fragility criteria, which in this case, I just look at just one attribute function, minimize k, subject to this attribute smaller then T plus kappa, this gamma, this epsilon, which this penalty term, right? For all Z in the support set. Okay. Now, the tractability here depends on a few things, right? It depends on this. If this function is a saddle function, right? Now it's convex in X, concave in Z, and this is no problem. You get a very nice robust optimization. You're not going to, but remember we focus on the polyhedral function, the polyhedral attribute function, you don't get that, unless it's a phi. Beyond a phi, right, this is going to be a difficult problem to address, right? Yeah. So it also depends on what is this this prediction matrix, disparity matrix is, and also so there are three things that needs to come together, right, so that you get a tractable formulation. Okay. So I'm going to focus on a simple one, right? This is what we were proposed in the paper, right? Just look at the simplest case that will make this work in a tractable way, right? I'm going to keep the L1 norm that I use that is similar to the price of robustness, right? The same disparity matrix over there, right? And I'm going to relax the support set. Since support is not necessarily easy to estimate, let me just put it as Rn. Right, you might feel uncomfortable doing it for robust optimization, but think about it, right? In stochastic programming, right, the most common, or stochastic analysis, right, the most common random variable that you use is actually the normal distribution, right, where they are unbounded support. Remember in the we use a lot more in robust optimization with the support set. And sometimes the issue is that when the solution can be very sensitive to how you estimate those support sets. This could be an issue because estimating those parameters could be an issue, right? So let me just try to remove the support set, right? It turns out that if you remove the support set, you can find an exact reformulation here without any approximation, right? You look at this, that is the first part of it, right? This part is very similar to the deterministic problem, right? Evaluated at the predicate value, right? Then you have a set of constraints over here that relates to, in this case, a solution, a potential solution, right? If the solution deviates in the direction of the the extreme points of the one norm, right? I'll explain that more in detail. But by and large, you look at it, it's just a single linear optimization model with some additional variables over here. And a lot of times, this is going to be so if D is a diagonal matrix, right, you're going to get very sparse structure, right? I'll show you that you can actually reduce this to very simple problem, depends on the structure, right? So the intuition behind this is actually quite simple, right? So if you look at here, the fragility measure, right? I can actually bring this thing, introduce a new variable, listed variable, and put it in this cone, right? And these are two identical reformulation, right? Except if you look at now, this is like a robust counterpart, right? And you know that this function f x z minus kappa u smaller than tau, this is actually convex, jointly convex in z and u, right? So you have a convex function, right? And you want to maximize z and u in this cone, right? So what you get is that you expect solution to be at the extreme points and extreme rays. So you just need to look at the extreme point, extreme ray. How many extreme points are there? When you use one norm, there are only 2n. Extreme rays, there are only 2n, right? So that's the gist of it. So I only need to eliminate 2n of them, right? So that's the idea, right? It seems to be quite easy, but when you try to prove it, right, it turns out that it's not as clean as we want. We want it to be a clean proof, but it turns out that there are issues at the limits that we need to take care, right? But it can be done, right? I do wish the proof could be simpler, right? If they are simpler, if someone has simpler proof, let us know. We don't really know how to simplify the proof further, but a simpler proof would in terms of teaching this approach should be easier, right? So I want it to be as simple as possible, right? So let's look at how this will look like, say, in a manufacturing problem, right? And in this case, I look at deterministic manufacturing problem. It's the similar example I have in the price of robustness, where the uncertainty just focus on the A matrix over here, and how it impact the Z is just components-wise influence, and that's why you have a diagonal sigma M over here. Here, if you look at the robust satisficing model, right, it becomes a very simple linear optimization model, right? You have the same, almost the same constraint. You have the same constraint as a deterministic problem, right? Except that the objective is now, right, I'm maximizing it. I need it to be greater than V minus gamma, right? So the greater the gamma, I have more flexibility in terms of, I have more, the solution will be more robust in that sense, right? And I minimize this subject to this constraint. If you notice, I did not introduce any dual variables. It's just more constraint, right? I think it's easy to articulate this model without having to introduce dual variables reformulation, right? And this is something that I feel that can be easily implemented. So one thing nice about here is that if you teach linear optimization to undergraduate, you realize that a lot of the solution will be the number of non-zero solution will be equal to be at most n. Sometimes it doesn't really make sense, right? But this model will try to ensure that all the solutions are the solution is non-zero. You encourage a non-zero solution, so a more diversified solution, right? Compared to focusing on the extreme point where you would get most of the values to be zero, right? In the basic feasible solution. So let's look at a project crashing problem, right? When you apply this to a project crashing model, right, assuming that all the Z is the D matrix is a diagonal matrix, right? What you get is also a very simple linear optimization model, right? I think if you work on project crashing using robust optimization, the way to do is use decision rule, right? You use decision rule, right? You are going to come up with a very large linear optimization, right? That might be okay for solving small problems, but you are looking at project networks with thousands of jobs and so forth, large-scale project network. Using those linear decision rule will be a bit problematic, right? So here in this case, it almost has the same form of deterministic problem. There's no introduction of dual variable for this particular example, right? Now, I'll briefly talk about the D matrix, right? The normalization matrix, right? And the D matrix is crucial in the fragility criteria, right? And suppose, hypothetically say, suppose I have prediction data, right? Someone who predicted the outcome, and I have historical data on how well they performed, right? Based on their prediction. So suppose this data, right? Empirical data on those things, right? I'm not going to assume a distribution model. I just use those empirical data, right? And those predictions can be from methods, machine learning models, and so forth, and they can be biased, right? And that always happens. Someone give you a value, you optimize over it, right? Suppose that information on how that performed, that potentially can be used to estimate what matrix that you would use. So with that, let me just define U to be the difference between the predicted and the actual inputs. So I have an empirical distribution of this guy, right? So it turns out you can choose your own profile, as follows, right? You can choose your own profile. So let beta be increasing function, right? Increasing function or convex function, right? Non-negative. So that when the expectation of this, when evaluated on the empirical distribution, is smaller than 1, right? For any matrix that satisfies this, it's easy to show that the probability of the attribute function, right? Suppose X is a feasible solution, or X feasible solution and kappa, right? This is the fragility level, right? The probability of the attribute function evaluated on the random outcome, right? Being greater than target plus the fragility multiplied by R is smaller than 1 over eta R for R greater than 0. So in other words, you can set your own profile on how confident the solution will be to achieve within that level of target violation, right? So that is something that you can set. You can choose eta to be a linear function, quadratic function, and exponential function, right? So that there's some design flexibility given. I'm not sure what will be the best, but there could be, I think some exponential function could be interesting, particularly if you have different set of data that you strongly believe there's independence, but they may not, the data may not be in the joint form, right? In this case, I assume that you have a joint, you have a joint distribution in terms of the empirical data. But sometimes, in a lot of cases, you don't have a joint distribution. You have an independent set of prediction from somewhere, and one combine together using approach, right? If you use exponential, you can split them up because of the moment generating function, right? But so there are some flexibility that you can use to do this. And now, how do you decide D, right? I didn't touch on it yet. If you look at it, I would technically like this fragility measure to be as small as possible, a lower value, because that kind of gives you a tighter bound, right? How do I do so? If I try to maximize, if I add D as part of decision variable to do this, this will be a decision-dependent uncertainty set that you're not going to get tractable approximation. Perhaps in some cases, but in most cases, you're not going to do so. So what we do, but you look at this problem, right? If I look at this, this is a robust optimization model, right? And I can just, now I introduce, I bring this norm from here to the ball, right? Allow this ball to be any size, right? But if you fix the size, right, for a given size gamma, right, the smaller the uncertainty set, the better it is. That will give you a lower value of kappa, right? The lower measure of fragility. So what you want is perhaps one that has a smaller size, right? How do you do so? The easiest way is to minimize the volume. Minimize the ellipsoid that contains this ball. So you have this ball over here. You try to minimize, and this ball is actually a polyhedra. You try to minimize the volume of an ellipsoid that covers this ball, right? It turns out that this can be written as a semi-definite optimization model, right? Minimum volume covering side, right? And it's not a difficult problem to solve, right? And you can technically extend this to asymmetric distribution, which we mentioned in the paper. We have not tested this out, but it seems to be an interesting idea that you can actually do it from, you can actually perhaps use prediction data to determine how this D matrix should be, right? You can add constraint if you want a diagonal matrix, then this will be much easier. Log determinant becomes the product of the diagonals, right? Which is a summation of a log. This will be a log summation, and the rest are just convex constraint, right? And of course, it depends on this. So you can basically write this as a convex optimization, log determinant. It can be addressed directly using Mosaic, right? And I think so that's all. Now, it turns out this approach can also, we covered on the two-period model, right? You can actually extend it to multi-stage decision-making model, where there is a policy, right? There's a non-anticipative policy to ensure that the total the total cost, right, is smaller than tau plus kappa multiplied by this penalty function, right? And because this is a multi-stage problem, I cannot write it as a simple attribute function, a function that minimizes over z, right? So I can't write it in this format, right? It turns out that you can actually write this fragility measure, right? Multi-period fragility measure as a linear optimization model as well, right? This is a tractable formulation. The same thing, you see this part is a deterministic model, right? And this part will be related to the direction that you can take, right? Respect to any deviation from the predicted value, right? This is interesting because I don't think I've seen any approach of addressing a multi-period model in a single linear optimization format, right? So it turns out that if you want to put a decision rule in it, right, you can actually do so, right? You can come up with a lifted affine adaptation, right, using this lifted variable, right, that relates to the positive and negative value of z, right? So sometimes I call this a segregated decision rule. So you get z, right? So look at it, look at how it deviates from the predicted value, the positive side, separated from negative side, R and the S, right? And use this as a decision rule, right? You use this approach, you'll get exactly the same solution, right? You get exactly the same model. The reason why we might want to do it, right, because sometimes writing in this formulation is easier because of the software that my colleagues have developed. Awesome, right? If you look at it, example, if you want to formulate a multi-period network log sizing problem, right? Network log sizing problem is complicated enough, but you look at multi-period, writing this down and putting decision rule on it, if you want to solve it, is tough, right? But using Awesome, right? Formulating, for example, the lifted uncertainty set over here is just this short statement over here. How it adapts here, right? It's just not many lines of code, and it's quite intuitive to see what it's trying to do. And the code over here is just a few lines over here. So there's some advantage if you want to model something quickly to understand whether it works or not. This could be a good tool to find out whether the solution makes sense from that perspective, right? So I have so numerical studies. I try to finish another maybe 10 minutes. Would that be okay? Right. Now, so for the numerical study, I want to go back to the basic and compare with the price of robustness, right? Price of robustness is everything is almost the same, except that I don't have the support set. And at the same time, this is a robust satisficing as opposed to a local robust optimization. So what do I lose for not including a support, right? So this is the same portfolio that is used in the paper, right? As the price of robustness, right? The same setup. The robust satisficing model here solves this problem. It's quite simple. It doesn't introduce any dual decision variable, right? And let me just go into this. So what I want to look at it, if you want to compare two solutions, right? It's difficult to compare a different choice in gamma, one uncertainty set, and another one is a penalty. You can't make, it's difficult to compare. But what you can compare is the efficient frontier, right? So in this case, the efficient frontier, in this case, I can look at the y-axis be the return. The x-axis will be a standard deviation that is the usual efficient frontier, right? The mean reach frontier defined in finance, right? And what I do is I vary the adjustable parameters for both problems, right? The red one is the robust satisfying approach, right? What I changed the gamma parameter. I can actually find out what this gamma parameters from this graph, right? The gamma parameter is actually the distance from the, in this case, the non-robust model, right, downward, right? You notice that that's how we this is what I use to justify the price of robustness. For small change in the price of gamma, it results in a significant reduction of the risk, right? A small change results in a significant reduction, right? You see that in the blue robust optimization as well, except that you notice there is a discontinuity from here to here, right? I'll show you in detail the difference. So for the robust satisfying, suppose I choose gamma to be here, right? I get a solution at this point over here. But for robust optimization, solution jump from here to here. There's a range of values that it doesn't use solution for, right? So if you look at the robust satisfying approach, because I ignore the uncertainty set, I use uncertainty, I cannot push down the robust satisfying value to 0. It's impossible, regardless of how I choose the target, because of unbounded support. So this is the lowest possible gamma I could choose, right? Beyond that, the solution doesn't change anymore, right? The risk, the lowest fragility is fixed at that point. It doesn't go down further, right? And the part of robust optimization is able to get another solution. This happens at the worst case, right? It includes the support information, right? The support information that gives you, that use a portfolio that invests in the worst possible, the stock with the worst possible predicted return, but it's also the least. It also has a risk, least amount of risk. So this amount of deviation. So this is something that if you take away the robust, you take away the support, right? The robust satisfying model cannot achieve this area, this level of robustness. But if you look at this problem, what will be a range of solution that you'll be keen in? I'm more interested in this range because that gives you significant reduction in the risk. I'm not necessarily interested in this range because for a small reduction in the risk, you have to pay quite a large price in terms of the return. So if you look at the elbow part, this turns out to be more attractive, and I possibly may not even need to choose solution in this area, right? If you need really the support, right, you need to justify, are you necessarily needed to choose values that is that extreme, right? So that support value will kick in, right? So this is another look at the budgeted uncertainty, right? When I changed the uncertainty set over here, you see that as I change gamma, right, you get different phases of solution, right? The first one is over here, then there's a sudden jump down, then there's a transition phase over here, then there's a constant phase and a jump over here, right? Which means sometimes it's not easy for you to match, right? How do you choose the size of that uncertainty set to give a particular performance, right? The second study I want to talk about is project crashing, right? That I mentioned before. Now, if you look at the deterministic problem, right? In this case, I have a project network that is highly symmetrical. There are 20 tasks, right, arranged in this network. The unit crashing cost is 1. All the predicted tasks have the same identical prediction time of 10. The deviation is just 10%, right? The crashing limit is 0.5, and the completion time is 60 days, right? If you solve the deterministic problem, all resources will be focused in the last 3 nodes, which makes complete sense because this is a task. These 6 nodes are all the jobs likely cause delay, right? If everything else is deterministic, right? This should work well, right? But suppose the task is only off, the prediction task is off by 10%, right? So suppose Z is a random variable, a normal distributed random variable. Sigma is just 10% from the mean, right? What do you think will be the probability of delay if you use the deterministic solution? Right. It turns out that this probability is just close to 1. The probability of delay is close to 1. Right. And you can improve the performance by having a lot more budget, right? Increase the budget. And you increase the budget by 100%, right? It reduces delay time, right, to delay probability to 10%. Right. So in this case, you don't get a modest reduction like you like to, right? And the only way to do this is through simulation, right? You can't see this from deterministic model, all right? And in this particular we can try other distribution, but somewhere around 100% will give you some nice reduction that you would want, right? Now, if you just compare the two solutions, right? So the robust, satisfying, and gamma will give you equal allocation of resource everywhere. You kind of look at it, this kind of makes sense because this is a symmetric example, right? In a project, if there's any delay over in any of the job, right, the completion time will be, the weakest link will be the one that has the longest time. So the only way is to allocate equal resources to all the jobs. And that can be a very expensive thing to do, right? It turns out that project management, this is kind of well known. So there's this study from McKinsey that looks at the project expenditure overrun, right? The G survey is 90% of project incurred cost overrun or delay, right? The average cost increased about 80% of original value. Right, and so I think one of the reasons is that perhaps they're using the wrong tool, they use deterministic tool to address this issue that leads to an underestimation of those costs. This could be one of the reasons that's why these are very difficult, important problems to solve. So I think I'll end. I concluded my presentation. So I think I think the thesis that I think the approach will fit in well as outcome raiser of robustness, right? But there's an important thing I'd like to mention. Although the idea is simple, it doesn't mean that it's the most effective. But what I feel is that it could be a good comparator to start with before we want to build more complex model, right? We don't need to implement the most complex model from the start, right? We need to implement maybe the simplest one. In area that you cannot address, perhaps we might want to use decision to add support and other things, right, to address that portion. But it doesn't necessarily need to use a full-fledged complex model, right, to address a robust optimization problem. Right. With that, I think I end my presentation. Thank you very much.